Hello, I'm John Doherty. This video discusses singular value decomposition. Some of the concepts are conveyed in slides. The mathematics, however, is done on a tablet. Now, it's not essential to understand all of the maths. It's the logic behind the mathematics that matters. As we will discuss, singular value decomposition gives us some unique insights into what calibration can and cannot achieve, and these insights are important. So are the insights that SVD can provide into related matters, such as the benefits and pitfalls of model simplification. These are discussed in another video. In this video we discuss singular value decomposition, how it can be used to solve an inverse problem, how it can be used to solve an ill-posed inverse problem, and what it can teach us about solution of that problem, that is, about model calibration. Everything that's discussed in this video is also discussed in the PEST book, which can be downloaded from the PEST web pages. All equations that we derive, the discussion associated with those equations is provided in this book. So at this stage we're talking about highly parameterized inversion. And we're representing our situation using this equation. As with other videos that in this series, this equation says that the action of the model on its parameters plus measurement noise is what we observe. We're assuming that the model is linear, that is, that the operation of the model on its parameters can be replaced by the operation of a vector, of a matrix, that is matrix multiplication of a vector. That vector K contains the parameters that we wish to estimate. It contains the hydraulic properties of the subsurface, and because we're working in a context of highly parameterized inversion, we don't care how big that vector is. Then, when we come to make a prediction with our model, we use another matrix equation. In that equation, we say that the scalar S is the value of a prediction that we care about. It is calculated from model parameters using the sensitivity of that prediction to those parameters encapsulated in the vector K, in the vector W. So here's the situation that we're dealing with when we're working in a highly parameterized world. Here's our equation again, H equals ZK plus epsilon. We don't care how many parameters there are. And just to make the maths a little bit easier throughout the rest of this presentation, let's assume that there are more parameters than there are observations. So the inverse problem is inherently ill-posed because it is not possible to estimate lots of parameters on the basis of a few observations. Because parameters outnumber observations, the Z matrix is long in the horizontal direction. Before we go on, let's remind ourselves of what calibration of a model should achieve. This was discussed in other videos. When we calibrate a model, we seek to solve an ill-posed inverse problem. To attain uniqueness, we have to regularize. We regularize in a way that achieves a number of things. Firstly, uniqueness, for that is the purpose of regularisation. Secondly, we attain uniqueness by seeking not just any solution to that non-unique inverse problem. We seek a solution to that inverse problem which is of minimized error variance. Hence, when we make a prediction with our calibrated model, predictions made by that model will also be of minimized error variance. That is, their potential for wrongness will have been reduced to its minimum by making that potential symmetrical with respect to the prediction we make with the calibrated model. In previous videos, we discussed manual regularization. So let's just revisit that topic for a few minutes. When undertaking manual regularization, we recognize the complexity of the real world as encapsulated in the vector k, but we decide that we're going to estimate a limited number of parameters encapsulated in a much smaller vector p. Therefore, there has to be a relationship between these two. This is normally fairly easily achieved. Consider the case, for example, where the parameters that we estimate, the elements of P, pertain to zones of piecewise constancy into which we subdivide the model domain. Here's 3 zones of piecewise constancy, and let us assume in this case that the elements of K pertain to each one of these cells. So the situation we set up, described by this relationship here, is simply that the value I assign to each element of K is that assigned to the element of P, which pertains to the zone in which the element of K lies. That simple relationship is expressed through this matrix equation. N is just a matrix with ones down part of each column. The ones tell us which zone each element of K lies in. When undertaking manual regularization, setting up this situation, setting up this equation will normally be a fairly easy task. Having defined how to calculate K from P, we can then go about estimating P. So here's our equation that takes full account of the complexity of the situation which we are dealing with. We then substitute NP for K, redefine X, the matrix which operates on the parameters, as Zn, and here's the equation on which we can base calibration of the model, where regularization is undertaken manually using this equation. We then create a situation like this, in which the matrix which operates on the parameters is no longer long and narrow in the horizontal direction, it's longer in the vertical direction than in the horizontal direction. There are fewer parameters than there are observations in the calibration data set. This is a necessary but not sufficient condition for uniqueness of estimation of those parameters. When I undertake regularization, of course, I have to ensure uniqueness of estimation of P. Once we've done this, we then follow the workflow, which is taken from another video. There's our new equation. We calculate a weight matrix on the basis of what we think are the statistical characteristics of measurement noise. Define an objective function, minimize it, estimate our parameters, estimate from the amount of misfit a coefficient by which we multiply the noise in the data, the calibration data set, and then derive an equation for the error variance of the parameters that we've just estimated. And everything hinges on the existence of that -1, that is, the creation of a matrix here which can be inverted. With mathematical regularization, we do things differently. We do not require that human intervention to define a simplified parameter set P. And the outcome of that is that, as we have discussed in other videos, we have a much better chance of in fact obtaining a minimum error variance solution to the inverse problem if we do it correctly. And secondly, we have enough parameters represented in the model to quantify the uncertainty of important predictions with integrity. There are two broad categories of mathematical numerical regularization. One is called Tikhonov and the other is called singular value decomposition. Singular value decomposition is the subject of this video. Each of these methods attain uniqueness of solution of the ill-posed inverse problem in different ways. Complementary ways, in fact. So here is our ill-posed inverse problem. Here is our matrix Z, long in the horizontal direction. Tikhonov regularization achieves uniqueness through making this matrix long in the vertical direction. It creates a situation where information used to estimate parameters, the number of items of information exceeds the number of parameters. A necessary but not sufficient condition to attain uniqueness. If this is done correctly, we can have a sufficient condition to attain uniqueness. But this is the subject of another video. This expanded Z matrix contains information on the parameters themselves. It can be values which we think those parameters should have based on expert knowledge. It can be relationships between the parameters. For example, that spatial variability of those parameters be smooth or minimal. But one way or another, we supplement the calibration data set with a whole lot of relationships which collectively pertain to all the parameters involved in the inverse problem. If we do that correctly, we can then obtain a unique minimum error variance solution for all the parameters contained in the parameter vector K. Singular value decomposition works in the other direction. It says we cannot estimate all these parameters. There are combinations of parameters which are uniquely estimable on the basis of this limited calibration data set. And there are combinations of parameters which are inestimable on the basis of this limited calibration data set. Let's reduce the inverse problem so that only these combinations of parameters are estimated. That is, those combinations of parameters which are in fact estimable on the basis of a limited calibration data set. Singular value decomposition works out what those combinations are and then it estimates them. Combinations of parameters that are not estimable on the basis of the limited calibration data set are not estimated, they are left uninformed, they retain their original values. But note that, as we will discuss, the singular value decomposition process parsimonises parameter space by evaluating combinations of parameters which are estimable and combinations of parameters which are not. Which do we use? Both. Under certain conditions, different conditions, both Tikhonov regularization and singular value decomposition, called SVD for short, can provide a unique solution to an ill-posed inverse problem which is of minimized error variance. Singular value decomposition can also guarantee unequivocal numerical stability in achieving a solution to that inverse problem, which is why we should always use it. Ticking off regularisation, however, allows us to pursue a minimum error variance solution for that inverse problem in more pleasing and more flexible ways, which is why we should always use it. Normally, we use both together when calibrating a groundwater model. Before talking about singular value decomposition itself, I want to spend a few moments talking about the null space. In doing so, I'll write the equations down so that they appear on the screen as I talk about them. I find that looking at equations as they evolve helps me to understand them a little better. I hope this works for you too. Let me start off by writing our fundamental equation. H equals zk plus epsilon. For convenience though, we're going to ignore measurement noise in this discussion, so I'll erase that term. The matrix Z, I'll also assume, is long in the horizontal direction. Therefore, we are attempting to estimate many more parameters than we have observations. That inverse problem can only be non-unique. Now, by definition, if I can find a vector delta k such that z delta k equals 0 and delta k is non-zero, by definition z has a null space. Suppose now that I have found a vector k hat which is a solution to the inverse problem. If that's the case, by definition zk hat equals 0. Now let me add these two equations together. I obtain h equals z k hat plus delta k. This tells me an important thing. If a matrix has a null space, if there is any non-zero vector delta k for which z delta k equals 0, then if I can obtain a solution to the inverse problem, I can add one such delta k to that solution to obtain another solution to the inverse problem. That is, if Z has a null space, solution to the inverse problem which it defines is non-unique. I want to discuss a concept called the generalized inverse. I'll write that down. Generalized inverse. So here's my original equation, H equals ZK. Now suppose one way or another I've obtained a solution to that inverse problem, a k hat. Hence H equals Z k hat. And let me define the matrix which allowed me to obtain that solution as the generalized inverse. That is, k hat equals Z negative H. Let's put aside for the moment how I obtain a generalized inverse, but let me denote it as Z negative with the negative superscript denoting generalized inverse. Now, let me substitute this equation into here to obtain H equals Z negative, H. But H equals ZK hat, so making that substitution, ZK hat equals Z negative, ZK hat, which gives us the definition that mathematicians use for the generalized inverse. That is, Z equals Z negative, Z. This is the definition of the generalized inverse. Now, contrast this with the definition provided in another video for the inverse of a square matrix. If a matrix is square, it may or may not have an inverse, and we denoted that inverse as a to the negative 1 as the inverse of A. And the mathematical definition of the inverse of a square matrix is this. Somewhat different than the definition of the inverse of or the generalized inverse, but it's readily apparent that if the matrix Z is square and invertible, then this equation still applies. So let me take this equation, let me take this equation and multiply by A negative 1, A equals IA equals A. So it is apparent that the inverse of a square matrix is just one particular instance of the generalized inverse of a matrix which does not need to be square. Let me now move over to this side of the tablet to extend the discussion. We'll start off with our fundamental equation, H equals ZK. Now suppose that I've found a generalized inverse. Suppose that I've solved for K hat. I've solved the inverse problem to obtain K hat, which equals a generalized inverse times my observation vector. Let me now substitute this equation into here to obtain Z negative, ZK, which I'm going to write as RK, where R has a special name. This is a resolution matrix. So let me draw a picture of this. I've got K hat. These are the parameters that I've just estimated. I've got my resolution matrix, square matrix, and I've got the parameters which exist in the real world. So that's R and this is K. And we have R equals Z negative, Z. Now the resolution matrix is quite informative. Let's go up here. And remember what happens when we multiply a vector by a matrix. Consider the ith element of k hat. That's ki hat. To calculate this from the vector k, and I've made a little mistake here which I'll rub out, this is the real world vector on this side of the equation. I will never know k hat. I'll know k hat, but I'll never know k. To calculate k hat from k, if I ever could, I would go along the row and down the column, that is matrix multiplication. What this tells us though, even though I'll never know k, and all we know is k hat, so we never know k, this is the real world properties of a complex geological medium which we'll never know. All we can know is k hat. I can never know k, but I can know the relationship between k hat and k. So the ith element of k hat is obtained through going along the row, down the column, and then this ith row of R, in carrying out that linear operation, can be viewed as obtaining a weighted average of the elements of k to calculate k hat. It can be shown that the only way that the resolution matrix will equal the identity matrix is if the Z matrix is square and invertible. And of course that won't happen if a problem is ill posed. So in general, we can't say that ki hat equals ki. What we can say is that the relationship between ki hat, what we see in the calibrated model, and k, the parameter field of reality, the relationship between the two is a complex averaging operation whereby ki hat is a smudged version of a lot of k's over here. This is the simplification mechanism that makes it possible to obtain k hat, and the outcome of regularisation necessary for uniqueness is that the estimated parameter field k hat is a smoothed, simplified average version of k, and that averaging process is expressed through various rows of the resolution matrix. And that matrix cannot be the identity matrix unless we have a well-posed inverse problem. Finally, let us look at a very special generalized inverse called the Moore-Penrose pseudo-inverse. It can be shown that if I have an ill-posed inverse problem, out of all the generalized inverses that allow me to get various non-unique k hats, there is one generalized inverse which gives me a special k hat. The k hat that I obtain in using this inverse is unique. The generalized inverse itself is unique. And it obeys a set of equations which give it a certain amount of symmetry. These equations are as follows. Z plus, and sorry, let me rub that out. Z plus Z, we give this inverse a special name, this pseudo-inverse, the Moore-Penrose pseudo-inverse, and we give it a special symbol. We give it a plus superscript instead of a negative superscript. That's the first equation that it obeys. Well, it is a pseudo-inverse. It must obey that equation. Then we have Z plus Z plus, equals z plus. So there's a symmetry relationship. Then we have two special relationships. ZZ plus transpose equals ZZ plus, and Z plus Z transpose equals Z plus Z. This says, of course, that the resolution matrix is symmetrical. Now it can be shown that the Moore-Penrose pseudo-inverse is not only unique, but the parameter set k hat that we obtain through application of that Moore-Penrose pseudo-inverse gives us a k hat whose norm is the smallest of all k hats that solve the equation zk equals h. So this is the solution to the inverse problem of minimized norm. Under certain circumstances, that can be shown to be the solution to the inverse problem, which is of minimized error variance. This solution is the solution to the inverse problem that we obtain through singular value decomposition. Now let's look at singular value decomposition in detail. Here, as usual, is my basic equation, and here is a pictorial representation of the matrix and vectors involved in that equation. I now write the fundamental equation for singular value decomposition. Now, singular value decomposition applies to any matrix, regardless of whether it's long in the horizontal direction or in the vertical direction, or indeed even square. But just for simplicity, we will assume that Z is long in the horizontal direction. Any matrix Z can be decomposed into three matrices, U, S, and V, which have special properties which make their manipulation particularly easy. Let's look at the U matrix first. U is an orthonormal matrix. An orthonormal matrix is a matrix whose transpose is its inverse. Hence, UTU equals UUT equals the identity matrix. Another way of looking at this is to consider the individual columns of the matrix U. These individual columns form unit vectors. These unit vectors are orthogonal to each other. As such, they can be considered to form a new coordinate system spanning model output space. Now let's look at VT. VT, a square matrix, is the inverse, or the transpose, of the matrix V. But because V, like U, is an orthogonal matrix, its transpose is its inverse. Hence, VTV equals VVT equals I. Being an orthonormal matrix, the unit vectors which comprise its columns are orthogonal to each other. And orthonormality means that these vectors are indeed unit vectors. Because they're unit vectors, because they're orthogonal to each other, they can be considered to comprise a new coordinate system spanning parameter space. Under certain circumstances, it's easier to use this coordinate system than the original coordinate system comprised of unit vectors pointing in the direction of the elements of the k vector. Now let's look at the S matrix. This joins U to V, T. Off-diagonal elements of S are all 0. The diagonal elements down here are all positive. They start at the high values and always decrease as we go down the diagonal. Perhaps they decrease to 0 somewhere down here. Perhaps we simply run out of room. So here's our situation. We put in the V matrix right side up just to make what happens next easier to understand. Here are the diagonal elements of our S matrix. And consider that they run out at the bottom of the matrix, or we could draw this line where they become 0. But in either case, we can partition this S matrix, or truncate as it's sometimes called, at the point where singular values either become 0 or simply run out. At this same point in the V matrix, we can also partition. So if we have 50 elements here, we will have 50 columns here. And this partitioning of the S matrix leads to a partitioning of the V matrix, which is effectively a partitioning of parameter space into two orthogonal subspaces. The V vectors on the left side of this truncation line, this partitioning line, span the so-called solution space. Its orthogonal complement, spanned by the V vectors on this side of the truncation line, span the null space. And here I'm defining the solution space to be the part of parameter space which isn't the null space. So singular value decomposition has allowed us to separate parameter space into two orthogonal subspaces. They are spanned by unit vectors v1, v2, etc., which do not pertain to individual parameters but to combinations of parameters. A new coordinate system in parameter space, defined specifically in terms of an inverse problem that is being solved. If we have three-dimensional parameter space and our null space has one dimension, this is a combination of parameters that are uninformed by the calibration data set. If our null space has one dimension, our solution space will occupy the other dimensions, in this case 2. And any vector lying in this space is informed by the calibration data set and is therefore uniquely estimable. I can formalize this by actually giving names to these matrices that are formed from the partitioning process. S1, S2 on either side of the partitioning line, V1, V2 on either side of the partitioning line as it's represented in the V matrix. This allows me to rewrite this fundamental equation for singular value decomposition. But I can make explicit my partitioning of the S matrix and my partitioning of the V matrix. Doing the matrix multiplication, these terms separate out, but this one is 0 because by definition it contains elements. The diagonal elements of it are 0. All elements of it are 0. And the diagonal elements of S1 are non-zero. So I can remove this to obtain my original Z matrix expressed as U S1 V1T, and therefore this pertains only to the solution space. I've removed any mention of the null space because they are not needed. The vectors in this space are not needed to fully express the original Z matrix. Now let's move to the tablet and explain how these concepts can take us to a minimum error variance solution to an inverse problem. So let's start, as usual, with our basic equation. What I observe is the action of the model on my parameters, K, plus measurement noise. For the moment, I'm going to ignore measurement noise, so I'll write this as H equals ZK. But now let me expand Z through singular value decomposition so that H equals U S V T K. And as we showed a moment ago, I can dispense with mention of the null space to rewrite that as U S1 V1 TK. Now I'm going to attempt to solve for K, thereby estimating my parameter set. The first thing I do is multiply both sides of this equation by the transpose of U. So U transposed H equals U transposed U S1 V1 TK. But recall that U is an orthonormal matrix, so the transpose is its inverse. These cross out. Now let me multiply both sides of the equation that I now have by the inverse of S1. Now this is the only time that I have to take an inverse in the whole parameter estimation process. By design, I will be able to take this inverse because S1 is a diagonal matrix with positive elements down all of its diagonal. This inverse will exist, and this is one of the great strengths of singular value decomposition. So S1 negative 1 UTH equals S1 negative 1 S1 V1 TK. These cancel because one's the inverse of the other. Now I multiply both sides by V1 to obtain V1 S1 negative 1 UTH equals V1 V1 TK, which I am going to identify as the solution to my inverse problem. I haven't recovered K. What I've in fact recovered is the projection of K onto the solution space. So let me draw that over here. So I'll pretend that I've got a three-dimensional parameter space, little v1, little v2 spanning the solution space, and I'll pretend that vector v3 spans the null space. Somewhere out here in parameter space is the truth, is the parameter set k that I will never know. What I have just calculated, however, is the projection of k onto the solution space. That's k hat. And that projection operation, that orthogonal projection operation, is defined by the matrix v1, v1t. So I have estimated the projection of reality onto the solution space. That then becomes the solution to my inverse problem, because this is as much as I can know of reality. So let's write this down a little more formally. What I have estimated k equals v1 s1 negative 1 UTH. That's how I solve the inverse problem. And I have established that the relationship between what I estimate and what exists is an orthogonal projection operator. In this case, the resolution matrix is precisely that orthogonal projection operator. Another interesting thing is this. Here's my k hat. Now, k could be up here above the solution space. It could be down here below. K hat is my minimum variance estimate of k because it lies on the solution space. And by lying on the solution space and not above it or below it, I attain minimum error variance parameter estimation by virtue of the fact that I have made my penchant, my possibility of being wrong, symmetrical to the parameter set that I have just estimated. So at the one time, k hat is of minimized error variance and of minimum norm. Minimum norm because of all the other k hats that could have satisfied the equation, the original equation, that is, this equation here. All the k hats, any vector, any k vector that has this same projection onto the solution space will satisfy this equation. The one we have obtained and taken as our solution to the inverse problem is the k hat that lies entirely within the solution space, the k hat of minimum norm, the k hat of minimized error variance. Now let's bring measurement noise back into the equation. So here's the equation that defines what we're doing. H equals zk plus epsilon. And the solution that we have just obtained for the inverse problem is k hat equals v1 s1 negative 1 UTH. Let's substitute this into here. so that we have k hat equals v1 s1 negative 1 ut zk plus v1 s1 negative 1 ut epsilon. Now let's remember that we can write z as u s1 v1t and make that substitution, so that we obtain k hat equals v1 s1 negative 1 ut u s1 v1 tk plus v1 s1 negative 1 ut epsilon. Well, for an orthonormal matrix, the transpose is the inverse. Here's the inverse of S1. So we obtain k hat equals V1 tk plus V1 S1 negative 1 ut epsilon. So let's come back to the picture we've been using of our three-dimensional parameter space. Little v1, little v2, and little v3, the vectors which span it. Here's reality, which we will never know, our unknown k vector. That's what we try to estimate, v1 tk. But this equation says that our attempts to estimate it incur error because of the presence of measurement noise. So what we really estimate as our k hat is this vector, and there's two components to the error. It's this term and this term. But let's take that a little bit further and explicitly express parameter error. So let's take k from both sides of this equation. K hat minus k equals v1 tk minus k plus v1 s1 negative 1 ut epsilon. Now I'm going to make use of a very important relationship. v1 t plus v2 t equals the identity matrix. Coming back to this equation, I'll rewrite it as k hat minus k equals v1 t minus I k plus v1 s1 negative 1 ut epsilon. And if I make this substitution, I obtain k hat minus k equals minus v2 tk plus v1 s1 negative 1 ut epsilon. So what this equation says is that the error vector in my parameters that I've just estimated has two components. There's this component here arising from this term here, and this component arises out of the need to obtain a unique solution to the inverse problem. This is the cost of uniqueness. the fact that I must estimate not k itself, but the projection of k onto the solution space. And then once I'm in the solution space, I have a second component of parameter error, that arising from this term here, that arising from noise in the calibration data set. So I have an equation for the error in the parameters that I've just estimated. Unfortunately, I can't calculate parameter error because I don't know k, the real-world set of parameters, and I don't know epsilon, the realization of noise associated with my calibration data set. But I can calculate my propensity for parameter error. To do that, I use a relationship that we've used a couple of times in these videos. If a vector y is calculated from a random vector x using that equation, I just made a mistake here which I will rub out. If a vector y is calculated from a random vector x using this equation, then the covariance matrix of y can be calculated from the covariance matrix of x using this equation for propagation of variance. So, taking that down here, the covariance matrix of parameter error equals V2, V2t, CK, V2, V2t, plus V1, S1 negative 1, UT, C epsilon, U, S1 negative 1, V1. So this CK matrix, this is, as we've discussed elsewhere, an expression of our expert knowledge. This describes the innate variability of the parameters, as we see, born of site characterization studies and expert knowledge, and off-diagonal elements of this matrix can express spatial correlation between parameters, all from an expert knowledge, prior information point of view. This characterizes noise in the data. To make this equation easier, let me make a couple of simplifying assumptions. Let me assume that the covariance matrix of k equals sigma k squared I. That is, every parameter is statistically independent of every other parameter. Let me assume the same thing for measurement noise. Sigma squared epsilon I. If I make these substitutions, the equation becomes a little easier. Ck minus k, k hat minus k, equals sigma k squared. This crosses out with this now. Orthogonal matrices come to our rescue again. V2, V2t, plus sigma epsilon squared, crosses out, V1 S1 negative 2 V1t, and I'm sorry, this should have been a t up here all along. So now we started with an estimate of the parameters for our model. We've solved the inverse problem and estimated our parameters, and we've shown that what we've obtained is not reality but the projection of reality onto a smaller dimensional subspace, the solution space, which SVD has defined for us. Now we have a covariance matrix for parameter error. This expresses the potential for error in the parameters we've just estimated, and as we've shown, this arises from two sources. The need to simplify the parameter set that is projected onto a small dimensional subspace in order to obtain uniqueness, and the fact that there's noise in the calibration data set. Now let us make a prediction with our calibrated model. But first, let's write the equations that we previously derived over here. We start off with the basic equation. We derived an equation for our estimated parameters. And we obtained the error variance of our estimated parameters, our covariance matrix of error variance, using this equation. When we make a prediction with our model, we make a prediction S, a scalar, equals WTK. This is the vector containing sensitivities of the prediction to the parameter set K. When I make that same prediction with my calibrated model, I make it using the estimated parameter set. Therefore, my prediction has an error. And I can write that error as WT K hat minus K. Using our same old equation for propagation of variance, sigma squared S minus S equals WT covariance matrix of parameter error W. Well, I know that because I derived it a moment ago, so I can write the full equation for the error variance of a prediction that I make with my calibrated model. WT V2 V2TW plus sigma squared epsilon WT V1 S1 negative 2 V1T, and I'm sorry, this should have been a negative 2 here. Now let's look at the repercussions of this equation. I'm going to draw a graph over here. Now, this graph presents me with the problem of where do I truncate? How many singular values do I use in solution of the inverse problem? So I'm going to label this as number of singular values. Or I could have written it as my truncation point. If I truncate at 0 singular values, that is, if I do not calibrate at all, if I don't do any history matching, then the error variance of my prediction is equal to the uncertainty of that prediction without any history matching at all. So in that case, it is simply sigma S minus S equals the innate uncertainty of the prediction equals sigma K squared WTW. Because this V2T becomes the identity matrix when the null space is all of parameter space, because we're not doing any history matching. Now, As I include more and more singular values in the history matching process, the dimensionality of the solution space goes up, the dimensionality of the null space goes down, this term falls monotonically. At the same time, this term rises monotonically, and at some point it rises very rapidly because of that -2 next to the singular values. So that goes up like that. Sum the two together and we have this. If I can draw it properly, we have a minimum and then it goes up again. This then is the sweet spot. This is the point at which I have minimized the error variance of my prediction. If I go beyond this point, the singular values get small, the inverse of the singular values gets large, and my potential for error in any prediction I make rises rapidly. This is the point here at which overfitting starts. So, too few singular values, I don't get enough information out of the data, I don't get a good fit with the data. As I get a better and better fit and truncate at a higher and higher number of singular values, the error variance of any prediction I make with the model gets smaller. At some point, the information that I receive from the calibration dataset is not worth receiving because it is too contaminated with measurement noise. At that point, I am overfitting, and my potential for error in any prediction I make has actually started to rise. As stated before, this then is the optimal number of singular values to use when I solve the inverse problem. Okay, so far so good. We've found a minimum error variance solution to the inverse problem, but we have assumed that sigma squared k, we have assumed that covariance matrix of k equals sigma squared ki. What happens if this is actually not the case? Well, in that case, our claim to minimum error variance status of the inverse problem cannot be sustained. We actually have to transform our parameters until this relationship applies. So suppose that I have a set of parameters, k, and that prior knowledge, intuition tells me that the covariance matrix of k is ck, and that I've defined an appropriate ck. Let me subject ck to singular value decomposition. As a positive definite matrix, singular decomposition of ck can be written like this. Ck equals EF ET. E is an orthonormal matrix. Because ck is symmetric, positive definite, we can use E and E here instead of U and VT. F, of course, is a square matrix with non-zero diagonals, but off-diagonal terms are all zero. That's what singular value decomposition gives us. And the singular values are non-zero all through the matrix. F is invertible. Suppose that instead of estimating k, I actually do a transformation. Suppose that I estimate a set of parameters j, defined from k through this equation. Et k. Now, using our simple relationship that we've used so many times for propagation of variance, which I'll write up here again, if y equals ax, then the covariance matrix of y equals a times the covariance matrix of x, at. I can write then the covariance matrix of j equals f to the minus a half et e, that's the covariance matrix of ck e f to the minus a half. If I substitute that into there, I obtain the covariance matrix of j equals f to the minus a half et e f et e f to the minus a half. Well, E is an orthonormal matrix. Its transpose is its inverse. These all cross out, equals I. And so the covariance matrix of J equals the identity matrix, which is what I want. So ideally, if I'm using singular value decomposition to estimate parameters, I should estimate J, and then I can back calculate, it is easily shown, I can back calculate my K using this equation. K equals E f to the half J. Unfortunately, this presents us with some problems. Firstly, this is a pain to do. It's annoying. This transformation, by the way, that I used to obtain a J matrix that is whose covariance is the identity matrix, that is called the Cahunen-Louvre transformation. Cahunen-Louvre transformation. The reason why this is problematical is that all of this is based on a knowledge of CK. We'll discuss this further, but if I do not know CK, or I don't know it exactly, and I base my claim for minimum error variance on a transformation that's based on CK, so here's the transformation I do that's based on CK, and if I'm not right about CK, then my claim to minimum error variance status is lost. So singular value decomposition is very powerful in terms of the insights it gives us, in terms of the ability to solve an inverse problem with the inversion of a matrix that's guaranteed to be invertible. However, its Achilles heel is the fact that to claim that I have actually reached the point of minimum error variance here, I need to know CK. In practice, I know something about my site, but do I know enough about my site to come up with a transformation that allows this claim to be met? And furthermore, is the geological complexity expressible through a covariance matrix? In most cases, geology is a lot more complex than that. As we start on a new page here, I want to draw your attention to the fact that I spelt Kahunen incorrectly on the previous page. This is the correct spelling. What I want to look at now is the relationship between calibration using manual regularisation and singular value decomposition, or rather to the equation that we use if we'd done regularisation prior to solving the inverse problem. As usual, I'll start off with the equation that describes the system. Now, just to make the maths a little easier, I'm going to assume that C, the covariance matrix of measurement noise, is proportional to the identity matrix. Under those circumstances, using an equation that we derived in another video, we solved the inverse problem this way. ZTZ -1 ZTH. And of course, if we regularise manually, this inverse has to exist. Now, whether or not that inverse exists, whether or not the Z matrix is long in the horizontal or vertical direction, I can always subject Z to singular value decomposition and write it like this. Z equals U S VT. If I now substitute that equation for Z into here, I end up with this equation. K equals V S U T U S V T -1 V S U T H. I've left off the one subscript here, simplifying things a little, because if Z is long in the vertical direction, things are a little bit different, but different in no material way. Well, U is orthonormal, it crosses out. So K hat then becomes K hat equals V S squared VT, that's a squared there, VT -1 V S U T H. Now I apply the inverse. K hat equals, and recall that the inverse of an orthonormal matrix is its transpose, and that the transpose of a transpose is the original matrix. This becomes V S to the -2 VT V S U T H, crosses out, equals V S -1 U T H, and I obtain the same equation that I obtained by direct application of singular value decomposition. So, traditional inversion, as we've done up to now in other videos, based on manual regularisation, gives me the same equation as singular value decomposition applied to a well-posed inverse problem. Finally, I want to address the issue of measurement noise in a small way. The equation which we've been using up to now is this one. And I've always assumed, for simplicity, that C epsilon equals sigma squared epsilon I. Suppose that it doesn't. Suppose that C epsilon is not I, is not proportional to the identity matrix. As we've done in other videos, let me define a matrix Q which is equal to C negative 1 epsilon, or proportional to it. Now I'm going to take this equation and I'm going to multiply all sides, all terms of this equation by Q to the half. So I obtain Q to the half H equals Q to the half ZK plus Q to the half epsilon, which I'll rewrite as H dash equals Z dash K plus neta, where each of these terms is defined just through this equation. So in particular, neta, my transform measurement noise, equals Q to the half epsilon, from which I can write that the covariance matrix of transform noise equals Q to the half C epsilon Q to the half, and because of this relationship here, that equals the identity matrix. So what this tells me, and applying a bit of theory that we don't demonstrate here, that if I take account of the fact that measurement noise may be different for different measurements, then I have to use weights. And we've talked about weights in other videos. I give greater weight to measurements that I can trust, less weight to measurements I don't. Ideally, I should use a weight matrix proportional to the inverse of the covariance matrix of measurement noise. So if I use weights in the same way as we've talked about with respect to manual regularisation, I then transform effectively measurement noise so that the covariance matrix of measurement noise is the identity matrix. All the considerations we've discussed in previous equations apply, and I do end up with a minimum error variance to the inverse problem using singular value decomposition, provided I use a weighting strategy that adopts this precept. So let's conclude this video by reminding ourselves about the good things and the bad things about singular value decomposition. The good thing, the best thing, is the fact that when solving an inverse problem, it gives us unconditional numerical stability. The matrix that we have to invert is designed to be invertible. We will not have any problems with inverting that matrix regardless of the ill-posedness of the inverse problem. The chief disadvantage of singular value decomposition is the fact that its guarantee of minimum error variance solution to the inverse problem relies on having to transform parameters in accordance with what we conceive to be the probability, the prior distribution of those parameters. Now, by doing this, what we're effectively doing is that we're estimating, by estimating the elements of J, we're actually estimating basis functions which are the columns of the E matrix. That is, the eigencomponents of the CK matrix. So we're hardwiring into the inversion process an awful lot of knowledge that is not really knowledge. We cannot escape coming up with some idea of what the prior probability distribution of parameters is. The problem is, using singular value decomposition, we're taking that knowledge too seriously. The Earth will never be simple enough to express as a covariance matrix, yet we build in rigidity into the inversion process if we base that process on a transformation which will never be correct. It is far easier to use expert knowledge through Tikhonov regularization. Tikhonov regularization allows us to deviate from preconceptions of what CK may be and allow us to express the nature of hydraulic property variability as we think we know it in far more flexible ways. Hence, if we are going to pursue a minimum error variance solution to an inverse problem, with our claim for minimum error variance based on adherence to what we think makes sense geologically, the best way to achieve that is through Tikhonov regularization. So when we solve an inverse problem, we still need to use singular value decomposition because we still need numerical stability. Tikhonov regularization cannot guarantee us that numerical stability. However, to pursue something, a parameter field that is geologically realistic, or at least doesn't contravene geology as we know it, because the parameter field we obtain will always be a simplified version of reality, the Tikhonov mechanism for insisting that that parameter field not violate geological reality is more flexible than that we use through singular value decomposition, where enforcement of geological reality is based on a Cahunan-Louvre transformation. So we use them both together, singular value decomposition and Tikhonov regularization. Tikhonov regularization is the subject of another video. Thank you.